So in the previous video, we found in the fundamental theorem of calculus part 1 that there's a link or a tie-in between the definite integral of a function and that function's antiderivative. We had, in fact, this definition that said, if we let g of x, I'll put him back up there, is the definite integral from some place to some random variable x of some function given to you dt, it implies that the derivative of that function is actually the integrand itself, okay? So you can, if you're given a definite integral, for example, if someone says, hey, figure out a to b of some function f of x dx, okay? Or if we go back to dummy variables, these are placeholders, so I'll put it back in here as I might need that. Then what it says is you could say, well, I can compute different stuff. Like, so for example, if I computed, say, g of a, what that would be the antiderivative or the definite integral from a to, guess what, a of f of t dt. And we realize, well, if it's the same limit, yet another property of integrals, then that's equal to 0. And it doesn't say that I have to use g. I can use any antiderivative and mess around with this thing. So for example, if I decided to take, let's say f of x be an antiderivative of like little f of x, this implies that f of, let's see, no, wrong f, capital F. That implies that f of x is equal to this g of x, but they might differ by some sort of constant, okay? Then they do something silly. They just simply go, okay, let's see. If I go, for instance, f of b minus f of a, for instance, then what I've got is g of b plus c, right? Minus g of a plus c, okay? But that's equal to g of b plus c minus g of a minus c. Bye-bye c. And you know what? G of a is 0, isn't it? So what we're left with is the following fact, that if I take an antiderivative and I compute f of b, and then I subtract from it f of a, all I'm left with is g of b. By definition, what's g of b? G of b is the integral from a to b of your function f of x dx, okay? So look what we're finding, and this is what's so surprising, is that the definite integral, any definite integral, okay, if you can find its antiderivative, it's the difference between the antiderivative's value at b and the antiderivative's value at a. This remarkable formula is what you're going to use forever. Whenever you see a definite integral from a to b of some function, okay, it's equal to f of b minus f of a. F is an antiderivative of f of x. Okay, it is. You can choose any of them, but guess which one we're going to choose? We're going to choose the one that doesn't have a plus c or any kind of constant whatsoever. What does this mean to us? It means that we can take antiderivatives, and as long, I should say, we can figure out or calculate definite integrals as long as we can find their antiderivatives. So we can calculate definite integrals by using antiderivatives. The integrands by using an antiderivative, how about that, of the integrand. All that work we did in the previous chapter of finding an antiderivative is going to come into play now. Okay? So what we did on the last test is, hey man, this particular problem right here, it says evaluate the definite integrals using the fundamental theorem of calculus. What we just plied through was part 2, by the way. And it's the one that makes the most play for us. It says basically, if you're trying to figure out a definite integral, number 1, find its antiderivative. So we will. Number 1, find an antiderivative of the integrand. I'm going to go. I have a tendency. I could really go fast with this, and you will too. But if I go too fast, it's messed up. So watch. I'll do this. I'll go. Okay. I'm going to look at this up here, and I'm going to find the antiderivative. Remember the rules. If there's a constant, you put an x next to it. So that's just x where the 1 is. If I derive x, I get 1 again, don't I? Then I go minus 8 times x to the 3 add 1 is 4, divide by 4. Remember that rule? Plus 16 times x to the 7 add 1 is 8, divide by 8. And then we typically put a plus c. But with a definite integral, we don't. Instead, we go, we are going to look at the limits of 0 and 1, because the next step, number 2, is compute f of b minus f of a, and you are done. It's going to be a numeric answer. A definite integral is a number, right? It's that limit we take in the previous video. You take the limit, and n goes to infinity, and what do you get? And you get this limit. Well, in this case, if we clean up, we've got the following. We've got x minus 2x to the 4 plus 2x to the 8th from 0 to 1, we say. We're integrating from 0 to 1. Never mind pictures anymore. Never mind rectangles anymore. We're just going to compute. So this guy right here is our f of x. Remember, f prime of x is little f of x, which is the integrand up here. Okay, all in parentheses. So what we have to do is calculate what is f of b, which is 1 minus f of 0, making it clear for you. Because if I go too fast, you go, whoa, what'd you do? Because this is what it looks like. You go, well, if I plug in 1 into this function, this f of x function, I get 1 minus 2 times 1 to the 4th plus 2 times 1 to the 8th. Okay, and then you subtract from it, plug in 0, and you get 0 minus 2 times 0 to the 4th plus 2 times 0 to the 8th, which is, of course, all of that nonsense is just what? That's just 0 this time, isn't it? And what else? We've got, therefore, in the front end, we've got 1 minus 2 plus 2. Looks like the answer is 1. You remember that limit I did with you guys, and it took forever, and we had the n plus 2, n plus 1, n 2n plus 1, and I finally got the answer 6, and we estimated with 6 subintervals on a previous video, and we got 6.38, whatever it was. Okay. What I did to make sure I had the right answer is I did this. I integrated and I checked it. Okay, let's do another one. I think I have 2 more on the next page. So all of these are examples that I just plucked from the book. Either I invented them or I just copied his problem. Here's another one that'll freak people out. It's like, what do I do? What do I do? It's a product. There must be a product rule. There is no product rule in integration. There is no product rule. But what we have now, you guys, is a heavy-duty fundamental theorem of calculus part 2. It says you got to find the antiderivative, but if you can do that, you've got the definite integral. You got it. Isn't that weird? So you take a function, you derive it, you get the rate of speed. You take a function, you integrate it, and you're able to sum or find the area under a curve. Calculus is insanely cool. All right, for this one, we learned this before we learned the product rule, by the way. We learned on this one what you could do to help yourself out is distribute. So there's some tricks you got to play. So we'll rewrite this integral from 0 to 4. And now we have 4 square root of t minus t square root of t dt. And we're going to help a brother out. We're going to keep going with algebra and say, hey, I'm about to integrate, or anti-derive, I should say. And it's 4t to the 1/2. You see what I'm about to do? Minus, and this is t to the 3/2 power, I do believe, dt. All of that was just so that we can get ready to antiderive, which we're going to do right now. We're going to say this is equal to 4 times t to the 1/2 plus 1 all over 1/2 plus 1. I'm helping you out. Minus t to the 3/2 plus 1 over 3/2 plus 1. And when we integrate, and by the way, this is in t's, right? So these are t limits, and I write it down so I don't forget. So I'm looking for step 1, I'm finding the antiderivative. And what we're getting is that's like 3/2, so 2/3, so 4 times 2/3 t to the 3/2 power minus 2/5 t to the 5/2 power from 0 to 4. So this guy that we have here, and I'll write it again, he's equal to, say, 8 over 3 t to the 3/2 power minus etc., right? From 0 to 4. We now treat that as our function, our capital F. That's our antiderivative. So what do? Well, we plug the top limit in first. Did you see? We're going to go f of b. I'll write it out. It's going to be f of b minus f of a. We're about to do it, and here we go. So we're going to plug in 4. So it's going to be 8, notice the parentheses, 8/3 times 4 to the 3/2 power minus 2/5 times 4 to the 5/2 power. And then minus over here, 8/3 times, well, this is just 0, isn't it? Minus 2/5 times, it's 0 again, that's nice. So all of that is just 0. So that happens. But what do we have here as an answer? We have 8/3. And 4 to the 3/2 is 2 is 8. Okay, minus 2/5. And 4, that's 2, that's 32. So we have a nasty fraction to add up. We got 64/3, I wasn't prepared for this, minus 64/5. So you know what, let's be smart. You can use your calculator, but I'll take out 64 and I'll add 1/3 and 1/5 to get 15ths. So I think it's 5 minus 3 is 2/15. Yeah, it's 2/15, so it's 128 over 15, I think, final answer. Check my work and don't email me if it's wrong. Okay. All right, couple more. You try them. So do you get the pattern of what you're doing with this? Is you're antideriving and applying the antiderivative first to the upper limit, then to the lower limit. And that's how you do definite integrals, baby. That's it. All right, pause and try. Remember this guy? You can split it up into different fractions. There you go. All right, let me help you out. So, okay, cosecant squared. What's the antiderivative? Derivative cotangent. Oh, yeah, it's going to be minus cotangent of x. That's it. It's a one-liner from pi over 4 to pi over 3. Again, I haven't done this. So let's see. You know what? I can write it as minus cosine of x over sine x if I need to, and I do. And I'm going to apply, again, pi over 4 to pi over 3. I don't know this guy very well. Do I? I can, maybe I can figure it out. But anyway, we've got this one's interesting because it's got a negative. So it's going to be minus, and it's going to be cosine of pi over 3 to help out people over sine of pi over 3. Maybe you know your trick, maybe not. Watch this. Minus, and it's still minus. You need to know that lesson. Cosine of pi over 4 over sine pi over 4. And we're figuring this thing out. Okay, so what is pi over 3? Sine's the big guy. It's going to be a minus. It has a 1/2 on top, and it has a radical 3 over 2 on the bottom, and then plus. And this is where they're equal to each other, so it's just 1. So it's looking like an answer says 1 minus 1 over radical 3. Good enough. There you go. We did it. You see, that problem, we could not have done the limits on it. You know what I'm saying? Because what we worked on were polynomials. We couldn't have even done the one before with the square root, this one up here. What we did as a limit problem definition was a polynomial. And that was about all as far as we could go. We are now finding definite integrals, exact values, using this marvelous theorem. Okay, this last one, go ahead and do it. We have integral 1 to 3. This looks like we have y minus 2 minus 1 over y dy. Antiderive, y to the 2 over 2 minus 2y. What else? minus the natural log of y. No plus c, just 1 to 3. Thank you very much. And plug in. So we have 3 squared is, we're going to put here 9 over 2 minus 6 maybe. You're starting to do stuff in your head. Minus natural log of 3 minus, now we plug in 1, so we get a 1/2 and a minus 2 and a minus natural log of 1. So let's get rid of parens. We got 9 over 2 minus 6 minus the natural log of 3 minus 1/2 plus 2 plus natural log of 1. And what other things can we say about this? Good question. Okay. We have, therefore, let's see, we have 8/2. See these guys? That's 4. And then it's going to be equal to 4 minus 6 plus 2. So all of that is really just 0, isn't it? But then we have minus natural log of 3. And what do you have to say about natural log of 1? It's 0. So our answer is looking like, hey, we got a negative. Is that even possible? Yeah, it is. It's totally possible. In the next chapter, we'll talk more about that. It's called the net change theorem, and that's coming up maybe in a couple more videos. But there you go, and I hope that you enjoy doing your definite integrals. It's one of the best things to do in math is I got to integrate. You can do so much with this. The keys to the kingdom are now yours. You know now how to take these guys, how to find antiderivatives such as these. All right, we'll see you in section 4.